We've seen that electric charges place forces on one another. We know that there must be an equal and opposite force between any two electric charges. And right now we're going to lay out the functional or working definition for the effect that a charge has on its surroundings, and by extension, the effect that it would have on any nearby charges. So we're defining now what's called the electric field. We'll be using a symbol capital E. It is a vector field, meaning it has a vector value which could differ at each point in 3 dimensions of space and 1 dimension of time. You know of other vector fields already. You could imagine the wind velocity. If you step outside, you could define at every location in space and time a vector that would give you the wind speed, and in a sense that's telling you something about the force that a small mass would feel if it were placed at that location. Another related concept would be one that you saw last semester in University Physics 1, and that is the gravitational field. This is a vector field. You may not have discussed it in this context, but you were exposed to the idea that there was this gravitational force everywhere on the surface of the Earth, which points towards the center of mass. And that force vector was given by the mass times a lowercase g vector. Right? You probably only discussed it as a scalar quantity and then described its vector direction as down or towards the surface of the Earth, which is fine when you're close to the surface. Everything looks flat. Just ask the flat earthers. Here, on a global scale, you need to realize that g, the local acceleration due to gravity, is actually a vector field, and it everywhere points towards the center of the Earth. And you know ultimately that the value of g gets smaller as you travel farther away from the center of mass of the Earth. So you've seen vector fields before. This is contrasted with a scalar field, such as temperature, where the value of the field is given by a single number at each location in space. E is defined as the vector F divided by Q0, where F is the force that would be felt by a test charge Q0 at this particular location in space and time. So we usually see this rewritten in a problem-solving context. We might ask you, what is the force that a charge feels in an external electric field? So this F equals QE is really your second main equation after Coulomb's law. It's important that in a vector equation, you must always include the sign of the charge. Usually a test charge we'll be thinking of as a positive charge, but this formula will apply in any problem-solving situation, even when the charge is negative. So you can either memorize rules like this, or just think about the vector directions and the sign of Q. So if your test charge is positive, the force that it would feel in an external electric field is parallel to that field. And if the test charge is negative, the force that it feels is parallel to the opposite direction of the electric field. Another way of stating this, I'll use this term in class. We want to make sure that you do not believe anti-parallel meaning perpendicular. It is not perpendicular. It is parallel to the negative of the vector E. Electric field has to be specified. Are we talking about the field that's created by a charge or some external field where we don't necessarily care about its source? So you need to get used to placing a charge in an external field in the context of a problem. You understand that we're not asking you anything about the electric field of the charge itself, the test charge. There will be other situations where you need to solve for the electric field created by one or more point charges. In those situations, E points away from positive charges and towards negative charges. So a positive charge sitting in some region of space creates electric field pointing outward. We should even imagine that those electric field lines are beginning on the positive charge. Positive charge is the source of electric field lines here. And negative charges you should imagine as a sink of electric field lines. On their own, electric field vectors will terminate or point towards negative charges. We will look at a specific example so that we can quantify the size or the magnitude of the electric field that's generated by a single point charge first, and then we will look at the electric field at some location in space created by 2 point charges. So individual point charges Q create their own electric field. So let's set up, say, a system here where we have a point charge Q at the origin. We'll define an R hat vector which points everywhere away from that electric charge Q. So it's a radial vector. R hat points everywhere. It's unique and it's not unique at the same time. It is the direction radially outward from the point charge. At some distance r away from the charge that we're interested in, we're going to place a test charge Q0. And for the purpose of this derivation will keep the test charge to be a positive quantity. We're going to allow the original charge here to take on either a positive or a negative value. In the case that the original charge is positive, I'll label here a repulsive force. We can call it F plus, plus meaning the situation where Q is positive. And it will have some unknown magnitude. This is what we're trying to solve for. It will point in the plus r hat direction. In other words, it points away from the original charge. For the other case, we'll deal with second. We can imagine the situation where Q is negative. The electric Coulomb force is attractive in that case. So we'll call F minus now some magnitude F minus, and it will point in the negative r hat direction. In other words, the force points towards the original charge Q. Let's focus on the first part here. If Q is positive, what we want to know is the electric field created by Q. I'll call it E plus because we're thinking about the positive case. That will be, by our definition, F plus vector divided by the test charge, Q0. Well, this is a Coulomb force. We'll take Coulomb's law for the magnitude of F plus, that's K magnitude Q0, divide by r squared. It's the magnitude of the force. It points in the plus r hat direction. We need to divide that Coulomb force by the test charge, Q0. Because Q0 is a positive charge, the absolute value of Q0 is equal to Q0. Because Q is positive, we could drop the absolute value signs here and state that this is simply KQ over r squared in the r hat direction. In the negative case, the charge Q will create a field. We'll call it E minus, just to keep them separate in our minds, F minus over Q0. Again, we create the magnitude of the F minus force. It's K magnitude Q0 over r squared. This points in the minus r hat direction, and we need to divide by Q0. So again, absolute value Q0 cancels out Q0. But now, what is the absolute value of Q when Q is negative? You should stop and think for a moment. The absolute value of Q is negative Q. If Q is, say, minus 3 coulombs, then its absolute value is plus 3 coulombs, and plus 3 coulombs is equal to the negative of negative 3 coulombs. So we have an expression here, minus Q, getting rid of the absolute value, in the minus r hat direction. You see these minus signs will cancel out, and we have an expression here, KQ over r squared, pointing in the r hat direction. Well, this is great because now we have the electric field created by a charge q of any sign is kq over r squared, pointing in the r hat direction. You don't need to worry about the charge being positive or negative as long as you include it in this expression. The electric field for a single point charge is kq over r squared r hat. We're going to use language throughout the rest of the course. We'll say that this electric field falls off like 1 over r squared, or as the distance from that charge q increases, the electric field diminishes like the square of the distance. Let us look at one example now where we're dealing with two charges. Q1 and Q2 placed in the XY plane as shown. To show you now a simple sketch of the situation. We'll place Q1 at the origin, and we will place Q2 at a location which is a distance x away from the origin along the x-axis. We're going to go to an arbitrary location up here. We'll call it point P. It will be a distance r away from the origin. And that location P will be at the position y along the y-axis. So this side of the triangle here is y in length. So we have the hypotenuse relationship here. R squared is x squared plus y squared. We can also define an angle here, theta, which may become useful later. And the cosine of theta is x on r. The sine of theta is y on r. So the goal here is to determine the net electric field at location P, and I'm giving it a specific direction here which is based on some given numerical values that we're not going to be concerned with in this example. For now, we need to determine this electric field by finding the electric field which is generated by each charge separately, and then adding them as vectors. So this follows the problem-solving steps on page 13. We need to break up and solve for the x and y components of these vectors e1 and e2 separately. So let's find the x component of the e1 vector, which is going to be e1 cos theta. E1 is the vector produced by the charge Q1. We'll imagine that Q1 here is a positive charge, which would give us an E field pointing up and to the right. Using the derivation that we just showed, the electric field E1 has a magnitude of K, absolute value Q1, over this distance, capital R squared. So you can see that E1x will take on a value K, absolute value Q1, x over R comes from this factor of cosine theta, and our R squared is x squared plus y squared. So we really have R cubed in the denominator, which will look like x squared plus y squared to the 3/2. That represents the x component of the vector E1. To find the y component, we'll follow the same procedure using the sign. So E1y is E1 sine theta. You can take this same expression and just replace x with y for the sine. So we have here K absolute value Q1 y over x squared plus y squared to the 3/2. You can see in this configuration that the electric field E2, which is created by charge Q2, does not have an x component. It points down. So we only need to find here E2y. There's no angles involved. We simply use the distance y in our expression. K magnitude Q2 over that distance squared. So this is y squared. And because we'll say in this example that Q1 is positive, giving us that E1 vector, we'll just take Q2 to be negative so that its E field points towards Q2. So the y component here should be negative. The y component of the net electric field, say E net y, should be now the sum of E1y and the negative of the magnitude E2y. So we'll add these two together. Here, E1y minus the magnitude of E2 vector. You have those expressions above. To find the magnitude of the net electric field generated by both charges at location P, we'll take E1x squared plus E net y squared. Why is it not E net x squared here? It is. We just have no x component of E2, so the x component of the net electric field is simply the x component of E1. So we're just finishing the Pythagorean theorem here. You have, again, the expressions above. If you were given numerical values, you could calculate that out. And if we want to find the direction of the vector net electric field, I won't use theta, I'll call it a new angle phi. That's the inverse tangent of the net electric field y component over the net electric field x component. It's just E1x. So this is how you use vector superposition of the electric field in the case where there are more than one point charge to deal with. So you could do this with any number of point charges and find the vector superposition of the electric field at an arbitrary location, P.